Welcome to Pomodoro Joe for Monday, March 20th, 2023. Today we're doing LeetCode problem 605, can place flowers. It's an easy problem. You have a long flower bed in which some of the plots are planted and some are not. However, flowers cannot be planted in adjacent plots. Given an integer array flower bed containing zeros and ones, where 0 means empty and 1 means not empty, and an integer n, return if n new flowers can be planted in the flower bed without violating the no adjacent flowers rule. Then we have an example here where we have one flower on each end of our flower bed and we want to plant one new flower, and there are 3 empty spots, so we can plant one right in the middle and we can return true. Example 2, we have a flower bed also with one flower on either end and 3 empty plots in the middle. But we want to plant 2 flowers. Well, we can't really fit 2 flowers in, so we return false. Okay, seems pretty straightforward. So we will put 25 minutes on the Pomodoro timer and get started. And no, we won't be doing C++. We'll do Python. Okay, so this problem, being an easy problem, I'll go through it a little bit slower and I'll try to explain a little bit more about the process. So for this problem, we'll need to understand a few basic concepts of programming. The first one being arrays, or in Python, they're called lists. So this list is essentially a container that has a bunch of elements. So this is the representation of a list in Python. So every element in our list has an index. The index of the elements start at 0. So this first element here is index 0, then index 1, 2, 3, 4. So our flower bed has indexes 0 through 4. Now the length of the flower bed is still 5 because there are 5 elements in our flower bed. To access any element in our array or our list, we can use indexing, which we can say something like flower bed at index 0. So that's square bracket 0. This will let us access the element at index 0 in our flower bed. Now we can write to the element by setting it to something like 1, or we can read from the element by setting some flower or any type of variable to the element's value. So that's a quick introduction into lists, also called arrays in many other languages. Okay, so we'll have to go through our flower bed looking for essentially 3 zeros in a row because we need to have one spot to plant our flower and then an empty spot on either side. So we'll be looking for all these places where we find at least 3 zeros in a row. So the other thing we'll need for this particular problem is a loop. In our case, we'll use a for loop. So for loop is just a way to go through all the elements quickly. So we'll be able to say for every element in our list, we can get the element value. So a for loop basically looks something like this: for flower in flower bed. Actually, this is probably not the right name for it. You can name it anything you want. This is more like the plot in our flower bed. So this represents all the different plots in the flower bed. And for every time through our loop, so here we can just say print plot. So what this will do is for every element in our flower bed, it will take one element at a time and use it in here with the name plot. So in this case, it will print 1, 0, 0, 0, 1, and that's how this works. So we can run this just to sort of give you an idea. So of course we don't have the right answer, but here's our print, 1, 0, 0, 0, 1. So it's just printing out every element in our flower bed. Okay, so how do we actually use this? Well, we need to go through, find 3 elements in a row that are zeros, and that means we can plant 1 flower in the middle. So let's do that. Actually, let me hit reload on this so we can clear this out. Okay, so now that we know sort of the basic pieces that we're going to need for this, let's see if we can put it all together and come up with a solution. So we need to go through every single flower plot in our flower bed. So for we'll call it plot or flower planting plot. Well, they call it a plot here, so we'll call it a plot. So a plot is just a piece of empty land, or it doesn't have to be empty, I guess. A plot is just a piece of land. So for plot in flower bed, now we need to check to see if this plot is empty, and we also need to check to see if the plot on either side is empty. Unfortunately, just using this for loop doesn't give us any access to the plots on either side. So one thing we can do here, there's a function called enumerate. And what enumerate does is it assigns a number to every element in flower bed. So you basically wrap flower bed here in the enumerate function. Okay, so now what we get back, instead of just plot, we're going to get an index and a plot. So index will be the number or the index in flower bed of our plot, and plot will be the value at that index. So we'll get 0, 1, 0, 0, 0, or sorry, 0, 1, then we'll get index 1, 0, and then we'll get index 2, 0, 3, 0, and then 4, 1. So now if I print these, we should see what I just said. Let's see, this will be a little bit of fancy print. I'm going to use the format. I'm not going to discuss this in this video, but this will just print my index and my plot side by side. Again, this won't pass our tests, but this should print out every enumerated plot. And it does. So you can see we have our index 0, 1, 2, 3, 4, and then the value, 1, 0, 0, 0, 1. All right, so now we have our index, which means that we can access the plots on either side of this plot. So we can say our previous plot is equal to our flower bed at this index minus 1. And our next plot will equal, what do you think it's going to equal? Flower bed at index plus 1. So this way we get access to our current plot, our previous plot, and our next plot. Now there's something that I haven't covered yet, and that's bounds of the index, or bounds of our list. So in Python, this will actually work only because Python lets you have a negative index, but our very first index here will be 0. 0 minus 1 is going to give us an index of -1. Now in most languages, that will cause a crash. You can't pass in a negative index to an array. In Python, it actually wraps around to the end of the list and will give you the last element of the list, but that's not what we want. We want basically the very first element, or the element before this current plot. Now in our case, when we start at 0, there is no element before, so we need to do some checks here. So if index is not equal to 0, well then we can get our previous plot. And same thing at the end. We can't go past the end of our array, otherwise we'll crash. So if our index is less than the length of our flower bed, then we can get the next plot. Now this presents some problems, because if we don't have an index greater than 0, then this previous plot will never get set. Now that's a problem, because we're going to need this. We need to use this down here. So something like, when we actually do our check, remember we're checking for 3 zeros in a row. So we're going to say if the previous plot equals 0 and our current plot equals 0 and our next plot equals 0, well then we can plant our flower. So we'll need to actually keep track of some count. So we'll have some count out here. So we've planted 0 flowers so far. If we find a plot where we have 3, then we'll plant our flower. We have 3 zeros in a row, we can plant our flower. And now we actually have to modify our input list to reflect that we've planted something here. So now we have to say our flower bed at this index will now be equal to 1 because we've planted a flower here. And then when we get to the end, we return true or false. So we need to return true or false. Now in this case, we'll return if count is greater than or equal to n. So if we were able to plant more flowers or the same number of flowers as the number that we are trying to plant, then that will be true. Otherwise, count will be less than n, which means we can't plant the number of flowers we want, and we'll return false. Okay, and as I mentioned, so this presents a problem. This previous plot and this next plot, these only get created inside of these if statements, which means they're not necessarily here outside. So we'll actually need to create them with some default values here. So we're going to start with our previous plot at 0, which just means that if we're outside of our array, we'll just assume that there's nothing before our flower bed starts. So that means it's okay to plant at the edge here. Okay, so our previous plot, we can start at 0. If index isn't equal to 0, well then we're above 0, so we can check index -1. Now this index minus length of flower bed is another problem. So the length of the flower bed is actually 1 greater than our actual index values. So in the example, this is index 0, index 1, 2, 3, 4. That takes us to the end. So our last index is index 4. But the length of our array here is 1, 2, 3, 4, 5. So if the length of the array is 5, and if our index is 4, we'd be at the end. It's less, but we're saying 4 plus 1, that's 5. That's going to cause a crash. So we actually need to subtract 1 from the length of our flower bed. This is something that you'll have to get used to when working with arrays or lists. Arrays and lists are 0 indexed, which means that the last index into that array or list is actually 1 less than the length of that array or list. And same thing that we had to do with our previous plot. We'll have to have some default value out here. Okay, so this should cover it. Let's try this. And we seem to pass. So there are a couple of things we might want to think about, like the very edge cases. What happens if we get to the very end of our list? Well, will we still check it? It looks like we do still check it because we are creating this next plot equal to 0. Even if we don't get into this, we'll still be checking to see if that last index can have a flower in it. So this should work. Let's give it a shot. Okay, and we pass, although we only beat 30% for runtime. So we beat 30% for runtime and 94% for memory. Okay, that's the basics of this one. Hope you can try this one out. Now I'm going to jump back and let's see if we can do some optimizations and make this way faster. This is going to be a little bit faster and a little bit more complex, so I'm not going to explain everything, but try to follow along if you can. All right, so the first things we're doing here, we have some count, we have these if statements, these take up time. We may have reached our count before we actually get to the end here. Let's say this count, when we do +1, exceeds n. We could return true right here. We don't have to wait till the end to return. So that's one thing we could do. The other thing we're doing here is we're accessing each one of these flower bed plots multiple times. So let's see, index 1, for example. So that's the second element. So at index 1, so when we're at index 0, we access index 1 here. Then when we move to index 1, we're accessing it again here. And then we move to index 2, we're accessing it again here, because 2 minus 1 is 1. So we're doing these flower bed index accesses multiple times. We could probably cut down on that to save us some time. So let's try a couple different things, and we'll take this one step at a time. So how about in here? If we get our count greater than n, we can return. So if our count is greater than or equal to n, we'll just return true. That's going to save us some time. We'll just early return. Let's see if that still works. Okay, it still works. Let's see if it saves us much time. A little bit. Went from 30% to 34%. Cost us a little bit of memory. It's okay. The other thing that I don't like about this particular solution is we had to modify our input flower bed. So when we were checking for these plots, we say we're going to plant a flower here. We actually are modifying our input to say that we planted a flower so that the next time through the loop, when we check to see the previous plot, we'll see, oh, we planted a flower there. Now this presents a problem for me as a developer because generally you don't want to modify your inputs. You can in specific cases when the customer specifically asks for that, or when you specifically say that this function will be modifying this flower bed. But in our case, that's not true. There's no reason why we need to be modifying this flower bed. So that to me just is a bad practice. You shouldn't be modifying your inputs. So let's see if we can do this without modifying our flower bed at all. Well, one way we can do that is instead of accessing our flower bed over and over again, what if we just cached out or stored the previous values and the next values as we go? Now, I know you're thinking, well, how do you cache the next value? Well, we'll actually be looking back. So in this case, we're looking at the center element, and we're looking back one and forward one, saying, hey, did we have 3 zeros in a row? But we don't need to actually look at the center element to do that. We could be looking at the last element and say, hey, were the previous 2 elements 0 and am I 0? So in that case, we can just look at the previous element and the previous element. So let's do that out here. So we'll keep some previous element and some previous element. And in our case, the previous element, because we're starting at index 0, the previous element will be before our flower bed starts. The previous element will be our flower bed at index 0. And instead of going through our index and our plot here, we can ignore the index. And we won't need to enumerate our flower bed, but we will want to start on plot 1. So the reason why we start on plot 1 is because we've already set the previous plot to be plot 0. So the current plot will be plot 1, and we'll go to the end. Now this special syntax here, this is special to Python. When you say flower bed 1 colon, you're saying give me from element 1 all the way to the end. Okay, let's get rid of, let's get rid of all of this because we're not really going to use this stuff. Okay, so now we have our previous plot and our previous plot and our current plot. So let's see if our previous plot equals 0 and our previous plot equals 0 and our current plot equals 0. All right, we've got 3 empty spots. Now we can increment our count. And at this point we can continue, but no, that's not true. We can't continue. We've incremented our count, so now we need to actually plant that flower. So where are we going to plant this flower? We're going to plant it at the previous plot. So, whoops. So the previous plot is our middle plot in this case. So we're going to set our previous plot to 1. We're planting a flower there. And now we need to advance all of our different plots. So now our previous plot becomes our previous plot. And our previous plot becomes whatever's in our current plot. Okay, so now we can do this. The one tricky thing here is now when we get to the end, we get to our last plot. This plot might be 0. The previous plot might be 0, but we're not going to check the next plot out because we'd be extending past the end of our flower bed. So we actually need to do something out here where if the current plot is 0 and the previous plot is 0, then we can plant one more flower here at the end. And of course, we'll still have our same check. Okay, I think this should work. Okay, it seems to work. Let's submit that and see how we do. Oh, and I have something wrong here. Oh, because, right, we are outside of this for loop. So now instead of checking plot and previous plot, we've advanced everything here. So we need to check the previous and our previous. Let's try that one more time. All right, and that works, and it does so much better than our previous attempts. So our best attempt before was a 34% for runtime, 65% for memory. With this new algorithm, we beat 92% for runtime and 65% for memory. Significant improvement over the previous. Now there are still some things we can do. We can clean this up a little bit, couple things. Let's see, do I want to show you everything? Yeah, well, let's do one thing here. So one thing we didn't do that we did in our previous algorithm is the early out. So let's do that here. All right, let's see if this still works, and let's see if this saves us anything. This may or may not save us much. It actually doesn't save us anything. It's 89% as opposed to the 92% we had before. So even though you think this early out should save us something, you have to do this comparison for every time you go through the loop. That may or may not save you some time. It costs time to do this comparison, so something to think about. Something else we could try. We could set count equal to n to begin with, and then subtract 1 from our count every time. And then our comparison becomes whether or not count is less than or equal to 0. And then we'll have to do the same thing out here. Now comparing to 0 is fundamentally faster than comparing to a specific number. So this might actually save us a little bit. And we get to 95%. 95% for runtime and 94% for memory. Not bad at all. Now there's one last thing that I will try. So right now we're doing this if this is 0 and this is 0 and this is 0. This is a lot of conditionals. What if we just added these together? Because they should all be 0. We can say what if previous plus our plot. Now all of this should equal 0 if we can plant our flower. All right, so does this save us anything? And we could do something similar down here, but let's just try the first one to see if it makes any difference. All right, still works. We have 1 minute left. 97%. So we still, no, that's our best so far. We get 97% for runtime and 20% for memory. We do worse on memory. Yeah, we had a 95 for runtime, 94 for memory. Now we're at 97 for runtime, 20% for memory. I'd probably stick with the 95 runtime, 94 memory. All right, that's it for me. Hope you had fun. Hope you enjoyed this. Hope you learned something. Hope you can go out and write better code.